Hello nerd boys and girls.
This is Official Nerd Business.
Today we're going to take a look at Project Euler's problem number 34, and we will be doing so using Python 3. As you can see, I've already got the PyCharm editor open, and I've made our base template file. If you've been following along, you can recognize the run method, which is called if this is main, and which is also the entry point for whatever solution we're going to code up here. You can see the attempt number 1, which is called from run. We could later make other attempts and keep our code intact to see how our attempts evolve and how we can simply test performance by changing whatever we call here. And up top there's the description with the title, with the parameters, which is a blank line in this case. We are not going to take any parameters for this challenge, which is 145 is a curious number, as 1 factorial plus 4 factorial plus 5 factorial is 1 plus 24 plus 120 equaling back 145. Find the sum of all numbers which are equal to the sum of the factorials of their digits. Note as 1 factorial is 1 and 2 factorial is 2 are not sums, they are not included. So we are specifically looking for multi-digit numbers. And we'd really like to know if we take their digits to their factorials and add them back together, do we get the original number back? Now, before we do so, whenever I start up a new solution, I basically just copy whatever we previously had, and in our last solution we had this function for simplifying fractions. Now I get the feeling we haven't seen many fractions yet. In fact, we are not going to work with fractions on this particular challenge, but still I feel that this is a very handy function, and I want to place it in our LibEuler. So what I am basically going to do, cut this out of here, jump over to LibEuler, and right at the bottom I am going to paste this in. And as you can see, with all the other functions we've got in this library, there's the docstrings. So I'm going to add that for this particular function too. And PyCharm here is very generous in automatically generating this stuff. There's a description, parameter n, so wait, it was already indented. And here we have and return is, you can drop the reference to the library, and it's, oh wait, there's more here. Thought there would be. We no longer need the e dot because that would reference another module, and these functions are in this particular module. It was referencing to this module, so no longer needed. And it returns new numerator. Alright, now we've got that settled. We could go back to problem 33 and remove the method from there. In fact, let's do that. 33, where are they? Here we go. And the simplified fraction method here, we can just delete it, and we will get an error here now, but we can reference the Euler module, which is included at the top. We're just gonna run this one. I know it said 34 in the title. Quickly running this yields the right answer. If you look back at problem 33, you will see that 100 is the correct answer. If you are now wondering why, look back at number 33. So that's settled. There's also another module, or another, oh, not in this particular case. Alright, we cast this to string, right? Now there's something different I want to include in the LibEuler as well, something we've seen before, which is int to list. Previously we've been kind of muddling around. We will get an integer in, and we will return a list of digits, because we needed, for the 145 example we just saw, we need a 1, a 4 and a 5. And there's plenty more challenges where we need to get these digits. Unfortunately, with strings, if we were to get some kind of string here, we could simply say for character C or X or whatever you want to call it in our string, and now we will get each character once in order. But we can't do that for numbers. If we had this particular test case again, we can't say for each digit in number, because this isn't recognized as a series of individual digits, it's just one number, so this would fail. We would get the error, integer is not enumeratable or iterable, but we can make it a, instead of return, let's use yield in fact. So how are we going to convert this integer to a list of digits? I'd like to use the yield operation for this. So we are going to specify for each character in the string representation of our integer, we want to yield wait, this is particularly important in C. So I want to, we are casting to string, we are casting back to int. That's unfortunately unavoidable. It still seems sloppy, but it's now sloppy inside of a library, so we don't really mess up our code with it. Converts an integer to a list of digits. Wait, when we feed this a negative number, we will get an error for converting a minus sign to an integer. So we're going to drop the minus sign and always look at the absolute values. Also, this does need to be an integer, because if you get a decimal point in here somewhere, then we're pretty much fried. For now, this will suffice. If we get errors using this method, we will come back to fix them. Now, how do we use it? As said before, we want to get these numbers. So what we could do is set up a range for I in range. That's 1 and 2 were excluded. In fact, we wanted to look at 2-digit numbers. What is our upper bound? Well, we do not yet know that, and that's something we're going to look at in a second. So let's set it at 1000. And we simply want to loop over. So we have an x value now, or a digit value for d in d.int to list. Print I and d. I'm printing I here so that we can check back to see what number is generating what output. If we run number 34 without main byte, so plainly by itself, it should get into here. It does. it runs up to 999 as expected, and it prints digits 10, 11, 12, 13, 14, etc. So it really does what it says on the bottle. 145 again. Here we go. 145 is a 1, a 4, and a 5. Alright. So this works as expected. That's nice. And we are not, however, very much interested in this. We want to sum its factorials, and we want to do that from out here. We want to set sum of factorials to 0, and then we want to add to sum of factorials math isn't included yet. And the digit. And once we have all of them, then we want to say if sum of factorials is exactly equal to I, print as f. In our range from 1 to 1000, that is only 145. And before we start expanding this, I mean, we could make this 10,000, we could make this 100,000 and see when it stops generating new numbers. In fact, this doesn't seem to happen very often. Ah, there's a second one, nice. And in fact, if we start this off at 0, I don't think 0 should be a problem here. Yes, 1 and 2 also show up, but they aren't sums as said in the example, because they are just there's no second digit to sum up with, so we still want to start this off at 10. So this does what we wanted to do, but we are unsure of what number to put here. And we can look at it from this perspective. To get an upper bound here, we can say if we have a 9, then we know what our corresponding factorial will be, right? We can not quite sure. Whenever I am not quite sure about one of these things and just want one simple answer, numerical answer, I start idle. And idle is a sort of Python console where you can just type in things and Python will run them for you. This is a more basic sort of tool than PyCharm is, but occasionally it's good to have something more basic at hand so that you can test one or two individual little things before you put them in your main solution. So let's see, or in fact I don't need to print, math.factorial for 9. That's quite a big number. 362,880. And there's 8, and there's 7. Hang on. There's 6, etc. And now that we know this, let's take this over back to our pie chart. Alright, so we know that 9 corresponds to this. And let's call this value factorial 9. Then we know that 99 will be decomposed into 9 factorial plus 9 factorial, which is basically just to let's just I'm gonna indicate this with f, right? This is just 2f. Then 999 is 3f. So while this value here keeps expanding at a rate of 10 to the power of something, and this power keeps going up. It's an exponential series, while the corresponding number of f's is just multiplication. So at some point, the number that we are breaking down into its individual digits and then summing up the factorials, even when they are all 9s, will give us per digit a smaller value than the order of magnitude increase implies. So this will run out, and at what point will that be? Again, we could set up a simple loop in idle, and I equals 1, and sum of f9 equals 0, and the order of magnitude maximum equals 0. Let's put this at, oh, hang on. Now let's see, while the order of magnitude is less than the sum of factorial 9s, I want to increase I, then I want to set the order of magnitude maximum to be 10 to the power of I minus 1. And I want to set the S9 to be alright. So here we are. We have an I of 2. That means that our order of magnitude will give us 3 digits, but we subtract 1, so we fall back into the realm of 2 digits. And if we take 2 factorials of 9, then we get this way larger number. Here is 999 against 3 factorials of 9, etc., etc., until we hit the order of magnitude 7, which gives us one more 9 than there are digits in this number. So this number grows, it's pretty big and it keeps on growing, but not quite as fast as adding orders of magnitude to this number. So we know now that if we take a look at this particular number, then this is the highest 9 factorial we can get. If we copy this and set this as our upper bound, we can delete all of this mark. We know that there are no paste. There can be no number bigger than this, because this is all 9s in the maximum order of magnitude. There are no numbers bigger than this that will have the attribute of their digits summing up to the digits factorial summing up to their original number. Once again, we run this. Takes a while, and it only finds these two numbers. Find the sum of all numbers which are equal to the sum of the factorial of their digits. So we want to have a return value here, and at the end of it we want to add I and return R. Now we're going to start up MainPy, I want to run problem 34. Now running. It took us 7 seconds, which is a long time, and I think we can improve on that. And it gave us 40,730 as the answer. And I can tell you, if you go over to Project Euler and you enter this number in the box for problem number 34, you will get a green check mark. This is the correct answer. That's 7.5 seconds. It's a bit on the slow side. So basically this code works, but let's see if we can do something to optimize it. I can think of 1 or 2 tricks. Can you? Let's see, we have attempt number 2 here, and we are going to run attempt number 2 when asked to do so. And basically what we're going to do here is we're going to make a list of facts, which is spelled differently than this, which is a list of factorial I for I in range 10. And what we are going to do now is not calculate these factorials, but look at the factorial map we've created here. There's a list here with all the factorials in it from the 0, because I will hit 0 when we start this, all the way up to 9, so that's each digit will have a factorial pre-calculated and stored in this list, and now it will only look at the list instead of calculating the factorials every time we call this with all the numbers and all the individual digits we have in here. We're going to run main.py again. 7.5 seconds. 7.5 seconds. Let's see if we can beat it. Not by much though. Took off nearly a second, but that's not a lot. I'm afraid it'll have to do. I was kind of expecting more of this caching method here. Maybe we'll come back at some point in the future to look at why this is so particularly slow. I know I'm going to look at it at a later date. For now, this is problem number 34. We did get our answer, and Project Euler asks us to do it within the minute, so we could have gone almost 10 times as slow and still get the answer in time. That's it for problem number 34. Don't forget to check out my GitHub if you want to look at any particular part of my source code. And I will see you again next time for problem 35.
Thanks for watching this video on Official Nerd Business. Don't forget to like and subscribe and click the bell icon. Did we discuss everything you wanted to hear, or did we miss anything? Any topics you want to hear in O&B? Leave your thoughts in the comments. See you next time.